In this unit, we're going to be looking at using the derivative to find maximums and minimums. So the things that we need to remember as we go through this is that you get a maximum when you change from positive to negative. So in other words, you're going uphill and now you're going downhill. And you have a minimum if you come from negative to a positive. And then we're going to look at why those are important and how they're used in the real world. So we're going to need to start with some theorems that we'll be referring to throughout this. The first is called the extreme value theorem. What it says is that if you have f, which is a continuous function on a closed interval from a to b, so remember it's continuous, no holes, then f has both an absolute maximum and an absolute minimum for some numbers in the round. So notice this one we have some hills. Now we do have two maximums, but there's only one absolute maximum. And then we have a minimum down here. This is an absolute minimum. Notice that we would have minimums at the endpoints as well, but this is an absolute minimum. On this one, notice that our absolute maximum is actually at an endpoint, while the absolute minimum is at the bottom of a hill. So you always have an absolute maximum and an absolute minimum. Even if you have a constant function, every point along there would be a max and a min. So could you come up with something to prove that theorem wrong? Can you connect those two dots in a way that you don't have a maximum or a minimum? Because even if I connected them straight, then that would be my maximum and that would be my minimum. Even if I had hills in the middle, I could have my endpoints as my max and min. Or I might have some hills that were taller than that endpoint or lower than that endpoint. Now, the next theorem comes as a result of that extreme value theorem. It's called Rolle's theorem. It says that if we have a function that is continuous and differentiable, and if our endpoints are at the same height, so here and here, so f of a equals f of b, and we're talking about the interval from a to b. So our endpoints are at the same height, then there is some number c within that round where their derivative is 0. Notice, every time we have a hill, our derivative is 0. Derivative is 0. Derivative is 0. So our maxes and mins all have a derivative of 0. Same here. Now there's only one point that has a derivative of 0. Derivative of 0. Constant function, every point has a derivative of 0. Now on this theorem, note that it didn't just say it was continuous, but that it had to be differentiable. Why? Well, we're saying that at some point the derivative is 0. So of course we have to be able to take the derivative. But differentiable, remember that means you don't have any of those sharp turns or cusps. So we have to be able to take the derivative the whole way through. Now for the following, state whether Rolle's theorem applies. So notice that Rolle's theorem, first it has to be continuous and differentiable, and then f of a has to equal f of b. In other words, our endpoints are at the same height. So let's look at some of these. First off, is f of x continuous? Well, it's a polynomial. F of x is continuous. So let's make a note of that. f of x is continuous and differentiable. So that's our first conditions. We need to make sure we say that. On the whole, on -1 to 3. So we have to make sure that in that interval, we are continuous and differentiable. Check. Now we need to check our endpoints. Does f of a equal f of b? So we need to look at f of -1. That's -1 cubed minus 2 times -1 minus 8. So we have -1 plus 2. That's 1 minus 8 is -7. We also need to see if that's the same function output as if we plugged in 3. 3 cubed is 27 minus 6 is 21. Minus 8. What is that? 13. So does Rolle's theorem apply? No. But what value is guaranteed to exist on this interval? Well, if it's continuous and differentiable, then it's going to have to go through everything. What we can say is that if we have our starting point is below the x-axis and we're ending above the x-axis, there has to be some c. There exists c on -1, 3 such that f of c has to equal 0. We have to go through the x-axis somewhere. On number 2, let's start with our conditions. Continuous and differentiable. Well, notice we have x minus 2 in the denominator. What's going to happen when x is 2? We're going to have a vertical asymptote. We're going to have a break in the graph. F of x is not continuous. So therefore, Rolle's theorem does not apply. What about number 3? Well, that's cosine. Now it does have some changes in our frequency and amplitude, but it's still cosine, definitely continuous, definitely differentiable. So we need to check our two values, right? So we need to check 3 cosine of 0, which cosine of 2 times 0 is 0. So, sorry, I skipped a step there. F of 0 equals 3 times cosine of 2 times 0, which would be 0, which is 1, so that would be 3. If we check pi over 2, 3 times cosine of 2 times pi over 2, which would be pi, which would be -1 times 3, which is -3. So does Rolle's theorem apply? No. Rolle's theorem does not apply. Last one. Oh, I should have said Rolle's theorem does not apply. The next one. This is also a continuous and differentiable function. I should have said that over there too. So continuous and differentiable. On 0 to 1. So now let's check our conditions. F of 0, it's going to be 0, 0. And then f of 1, it's going to be 1 minus 1, which is also 0. So we do have a point on this one that's going to have a derivative of 0. In other words, we're going to have a critical point, something going on. So I need to find the derivative, which this would be a perfect one for power rule. Subtract 1. We want to know when that equals 0. Now, my mind might work differently than other people, but the first thing I see are the fractions, and I'm going to multiply both sides of the equation by 3 just to get rid of those. And that leaves me with 2x to the negative 1/3 minus 1x to the negative 2/3 equals 0. Now, I know this negative means it's 2 over x to the 1/3, or the cube root of x. And if I add x to the 2/3, I'd have 1 over x to the 2/3. I'm just doing something a little different here. Kind of show you different ways to solve equations when you're not sure. So if I multiply both sides by x to the 2/3, I'd have 2x to the 1/3 equals 1. In other words, x to the 1/3 equals 1/2. Now notice, by doing this, I've discarded the fact that we're going to be using 0, because 0 would give me something undefined, and I don't want that. Now, x to the 1/3 is really the cube root of x, so to solve this and get x by itself, I would cube both sides. So x is 1/2 cubed, which would be 1/8. So at 1/8, our derivative is 0. So at x equals 1/8, f prime of x is 0. Now, if we plug that value back in, we can actually find out whether we have a maximum or a minimum at that value. If I plug that back into the original equation, I could find out if this x value gives me a maximum or a minimum on the graph. And we'll be getting into that more in a minute. But the next theorem that we need to make sure that we go over was proven around 100 years later. The mean value theorem says if you have a function that is continuous and differentiable, and there is a number somewhere, some x value, where the slope of its tangent line, the derivative, is the same as the slope between the two endpoints. Now, how is this a generalized Rolle's theorem? Well, in Rolle's theorem, we said that if the two endpoints were at the same height, then there had to be a point where the derivative was 0. Well, that's because if our two endpoints are at the same height, if I found the average rate of change between those two, it would be 0, which is the same as this. So the average rate of change is going to be equivalent to the instant rate of change at some point on the graph. Now this is the slope of a secant line. The slope of this tangent line is going to be equivalent. So, on number 1, polynomial, this is a quadratic, so it's definitely continuous and differentiable. F of x is continuous and differentiable on -1 to 3. So this time, we need to find the average rate of change from -1 to 3. And then there is going to be some point where the derivative at that point is the same as the average rate of change. So I need to find the average rate of change. So I need to take f of 3 minus f of -1 over 3 minus -1. And I like to go off to the side to do my dirty work. Let's see, f of 3 equals 3 squared minus 5 times 3 plus 7, 9 minus 15, -6 plus 7 is 1. F of -1, -1 squared, which is 1. That'd be plus 5, so 6, plus 7 is 13. So we have 1 minus 13 over 3 minus a -1, which is 4. So we have -12 divided by 4, which is -3. So there's got to be some point where the derivative at that point is -3. Well, let's find it. We definitely know how to take the derivative of f of x in this problem. Power rule, 2x minus 5. We want to know, when does 2x minus 5 also equal -3? It's going to be at x equals 1. So at x equals 1, f prime of x equals -3. What about on the next one? What function is that? Well, that's an absolute value function. That means I have a sharp turn. MVD does not apply. Even though this function is continuous, f of x is not differentiable at that cusp, so at x equals 2. Now, what if they had picked a different interval? They had picked something other than 0 to 4. Then we could have done it. Now let's take a look at this function, x plus 1 to the 2/3. Now this has a cube root in it. And if we actually look at this one on the calculator, I want to make sure everybody understands what this one's going to look like. So I've already set this up. I've already put x plus 1 to the 2/3 in the calculator. And looking at the graph, it has a cusp at -1, which is in the interval. So f of x is not differentiable at x equals -1. So MVT does not apply. What about in this one? Well, this would be a hyperbola with a vertical asymptote at -1. Well, beautifully, that's not in our range. So if we're looking at this set of x values, I said range, domain, -1 is not in there. So this is continuous and differentiable on that interval. MVT applies. That means if I find the average rate of change from -1/2 to 2, then I can find some point on the graph that is the same instantaneous rate of change. So let's look at f of 2 minus f of -1/2 over 2 minus -1/2. F of 2, that'd be 2 over 2 plus 1, that's 2/3. -1/2, that's going to be -1/2 over 1/2. It's going to be a -1. 2 minus a -1/2 is going to be 2 plus a half, which is going to be 3/2. 2/3 plus 1, that'd be 2/3 plus 3/3 would be 5/3. And a fraction divided by a fraction, we would take 5/3 times 2/3 and get 10/9. Now, how do I find the derivative when we have a fraction? Well, that's going to be the quotient rule. Quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top over the denominator squared. So this would be x plus 1 minus x. It's going to be 1 over x plus 1 squared. And I want to know when that equals 10 over 9. Oh, how nice, that's a fraction too. So I want to know when 1 over x plus 1 squared equals 10 over 9. Well, that's the same as x plus 1 squared equals 9/10. You take the square root of both sides. That'd be 3 over square root of 10, and then subtract 1. So do we have 2 points here that meet this situation or not? Well, if I take -1 and subtract anything else, I am way out of the domain here. So it's -1 plus 3 over square root of 10. And that is a safe stop. Next, the table below gives selected values for a differentiable function, f, and the derivative f prime. Now remember, if it is differentiable, that also means it is continuous. So I like to make a note, also means continuous. Because to make sure you use these rules right, you have to say first, before you can use these theorems, that it is continuous and differentiable. Well, for the first one, you only have to say it's continuous. But let's see what we have. So is there an x on the interval from 0 to 30 where f of x equals 15? Well, since we've been given the table, since f of 15 is 20, there has to be an x value where we've gone from, if we've gone from 5 all the way to 20, we've had to pass through 15. And that's intermediate value theorem. Is there a x on the interval from 0 to 30 where f prime is 0? Well, we start and stop at the same height. So of course there is. That would be Rolle's theorem. Or you could even say it's MVT. Is there an x on the interval from 0 to 15 where f prime is 1? Well, the only way we could check for that is to use MVT and check what my average rate of change is. So that would be checking to see if 20 minus 5 over 15 minus 0 gives me a 1. If it does, then that's MVT. Is there an x on the interval from 30 to 40 where f prime of x is 0? Well, since this is continuous and differentiable, notice that my derivative at 30 was 1, and my derivative at 40 is negative 1. That meant I'm going from positive to negative. So there had to be some point where the derivative is 0. Also, we can think of it as the extreme value theorem. You're going to have some place that is a max or a min in that interval. Is there a maximum value of f on the interval from 0 to 40? Well, of course there is. That's extreme value theorem. Is f of x equals 20 the maximum value of the function? Well, it does look like it's the largest one in the table, but what would be our derivative if it truly was a maximum? Shouldn't be 2. That means we're still increasing. So no. Is there an x value on the interval from 0 to 40 where f double prime, our second derivative, is 0? I want you to think about that one for a second. Could one of the theorems that we've been learning actually help us with this? Well, the problem comes in that we don't know if the first derivative is differentiable. We only know that the original function is. Now, if we knew that it was, we could take the second derivative. If it was, notice that f prime of x has a value of 2 when x is 0 and when x is 15. That means the average rate of change of the first derivative is 0. Therefore, the second derivative would have an instantaneous rate of change of 0. That would be Rolle's theorem.